If you listen to these additionally, that's fine. If you don't listen to these additionally, that's fine. I wanted to finish up some identification of the peripheral nerves, which I do not recall whether I started or not, but I typically overlap when I do these things. It gives me something to do. And I will show you where we are. So this was the PowerPoint 13D, the one that comes after all that peripheral nerve stuff, and of the cranial nerves, and these are the peripheral nerves. So rather than going through it, it's very elaborate in traditional anatomy and physiology. I have no idea if anybody in other labs does these things. I don't, but I'll give it to you. So, in a sense, effectively, they're all by definition mixed nerves because they're a combination of motor and sensory roots. You get sensory roots that come from posterior or dorsal aspect, motor roots from the ventral aspect. They intertwine, and as you will see, you get a variety of nerves that go to different, and they're not done yet. So most of the nerves that you and I will have a name for, the radial nerve, the ulnar nerve, are a mixture of multiple roots, of strands coming from multiple areas. There are 8 cervically. The interesting thing, typically nerves are numbered from coming out from the vertebrae, they come out below. So first thoracic vertebrae, T1, and the nerve associated with it comes out inferior to it or underneath it in the interspace below it. The only one, the oddball, is the cervical, because you have one coming up above the first cervical vertebrae. So, and there's only 7 cervical vertebrae, so the last one is 8. So you have 8, 12, appropriate for the number of vertebrae. 5 for lumbar. 5 because technically the sacral area has 5, and whether there's something that's from the coccygeal is variable. So each of the first 7 pairs exit the canal above, and these are the intervertebral canals, the small ones that are impacted, particularly by disc problems, which I have. And the last spinal nerve exits below it. So that's the oddball. So vertebrae C7 has a nerve that leaves above it and one that leaves below it, which makes it unusual. So everything else below, just anatomically. Because of the abundance of structures going to the upper, and we saw a little bit of this before, and the lower extremity, we have what are called enlargements. And this is classic anatomy, and you might have had this in AP1 when they talk about the cervical and the lumbar or lumbar sacral enlargement, and things like the cauda equina and terminale and all of those things. So, and again, they're a combination of motor and sensory roots, and it's not just one part. It's many, many strands. They're called rootlets, and that's what they look like. So you have multiple strands coming out, whether they're, and these would be, you can see dorsal rootlets, and you can see ventral rootlets. However, they've arranged this type of thing. The dorsal would be back here. The ventral would be up here. Because the vertebral bodies are always anterior to it. Okay, and the cauda equina, and then this is extra stuff that in graduate levels of anatomy and medical school anatomy, we look at these variety of branches that go to meningeal areas, the rami, which are little projections that go forward and backward. So a lot of the back muscles that you might feel, okay, the sensors that you get from them are coming backwards. They almost go directly backwards rather than forwards, or they intermingle. So there's a lot, and particularly so in the thoracic and lumbar regions, because you have a lot of what they call rami communicante. It's not a name that you have to know, that involve in sort of the intricacy, as it were, of the autonomic system. So this is a typical thoracic area, and you can see it comes out here, and there's all sorts of business. Some go to the back muscles, some go to the front, etc. Okay, I don't go too crazy about that. In general, okay, both carrying sensory and motor, and typically the motor material comes out ventral or anterior, and sensory comes in posteriorly. And with the exception of the thoracic area, which really supplies the chest wall, as the name would suggest, and the intercostal musculature, etc. Okay, all of these, so those nerves go directly to their target, as opposed to everything else forms a plexus. And again, in classical anatomy, you see this overlapping interdigitation, whatever word you want to use, this elaborate crossing network where parts go to different areas and eventually, for the most part, formed named nerves that are a combination. So the cervical plexus is unusual. There's C1 through C4 with maybe a hint of C5, and they're typically cutaneous nerves for sensation that you have here. And this is the big player, the phrenic nerve. The phrenic nerve has C3 and C4 and even a small portion of C5, which is unusual. The name tells you what it supplies. It is the major motor and sensory branch for the diaphragm. PHR for diaphragm, PHR for phrenic, how it derives its name. This is why one of the things when we see a cervical fracture, when somebody breaks their neck, okay, that the major area that of concern is breathing, because it's going to compromise them. So, and the best story about it, I saw one when I was a student, where, and it's very interesting how the story was, because this was an equestrian, okay, and she had fallen wearing, the headgear and everything else, broken neck, C3, C4. They were fortunate it was a very limited fracture, and we were not seeing signs of paralysis there. At that time, I have no idea what the technology is today. This was 47 years ago. They had, there were 10 of us moving her in such a way to position her for the neurosurgeon to come in and put what's called a halo in, okay, where they numb the scalp and drill into it and create, it looks like a halo. They suspend, and then they have a brace that suspends it to keep the neck elevated, almost like that. So we're all, if you move that individual the wrong way, it could be lost. Most famous story was the original gentleman who played in the movie version of Superman, a wonderful actor named Christopher Reeve, who fell off a horse, broke his neck, was paralyzed, completely quadriplegic, and ended up regaining a certain amount of, and that often happens, maybe little aspects of digital control, but eventually succumbed to respiratory complications. That's, he died X number of years afterwards of respiratory complications. So it's something we see a lot of. So this big guy coming down here, that's the phrenic nerve. Just remember phrenic for diaphragm. And all the other ones, again, classic anatomy, we learn all these stupid names. And spasms for hiccups is something like that. And then respiratory arrest, respirators, and the big plexes. The plexes that are classic are the brachial area, which is C5, C8, and a little bit of T1, even some other branches, obviously, as you can see here. And what was originally called the lumbosacral plexus. Now we divide it into lumbar and sacral. And we used to remember this. It goes roots, trunks, divisions, cords, and branches. So you made up some kind of mnemonic for RTDCB, which thankfully you won't have to do. So here you can see the roots coming out. You can see the crossover network that's there. And then the color chart really gives it away. You have effectively a posterior division that's in green and an anterior division that's in the yellow. And so there are 5 nerves that supply your upper extremity. And obviously there's a lot of other nerves that supply some of these areas you can just see by their names. Pectoral area, subscapular area, some cutaneous or nerves in the skin. These 5 are classic. Okay. You have the axillary nerve. The axillary nerve and the radial nerve are the 2, as you can see labeled in green, though it could be a better illustration, that have the axillary nerve is basically your big deltoid. Remember that muscle from AP1? Let's do this. It's a massive muscle. Its principal innervation is this. There's probably a little bit of trapezius that's associated with it as well. And then everything else, every other muscle on the posterior aspect of the upper extremity, every extensor, whether your triceps brachii, any of the extensors for the wrist, carpi ulnaris, carpi radialis, all those wonderful names, radial. And they'll give you a chart with this. On the anterior aspect, there are 4. Okay, you have the musculocutaneous here. Musculocutaneous is very specific. its principal innervation is the biceps brachii and brachialis. So your ability to flex. I used to demonstrate this, but I don't. My daughter's fiance they're bigger than my thighs. They go over at 5:30 in the morning. They work out every morning because they're buddies with the people who owned Alexander's Athletic Club over at Harvard. I don't know where she got that. So that's the musculocutaneous. The main nerve is the median nerve. Surgeons call it mother median. It goes right down here. When you get carpal tunnel, right here, and a lot of people have it over time. It's not just there. I mean, I can tap this, and I can feel just there, little funny sensations going into my fingertips. Over time, we get this. They've arranged keyboards and things differently to prevent that. Truck drivers used to get it because they put their arm on a vibrating wheel, and you always had to stop doing that. It was a classic kind of thing that went on. That's the median nerve. The median nerve basically supplies almost, other than that, all of the forearm and hand flexure musculature, with exceptions that, again, you study in more advanced levels of courses. For sensation, thumb, index, middle finger, and about half of your ring finger. So it's median, so it's from the ass, even though that's laterally, they've named it, well, I don't know. Okay. From an anatomical position, they call it the median nerve. The ulnar nerve, you're hitting your funny bone because of the groove that's there on the medial aspect, on the ulna, and that little notch that's there, and the nerve is very superficial, so we all whack it periodically, and it'll send jolts going up this way. Principally, that supplies the more technically anatomically medial aspects. So they give you a little look-see. They show you how these occur. Axillary, mostly deltoid. Shoulder, teres minor. It doesn't have the trapezius. Musculocutaneous, biceps brachii and brachialis, some other stuff. Median, most flexors. Pronators, allowing form to do this. Wrist and finger flexors, opposing your thumb. Ulnar, flexor carpi ulnaris, so there's a little bit on the ulnar aspect. Digitorum profundus, you could do this. The tiny intrinsics in your hands, etc. And the radial, essentially all extensor muscles, supinators, posterior skin. So I give you a diagram to reflect that. That's the actual axial plexus. I have seen years ago these do regional blocks and have the anesthesiologist inject in that area as a way. It's kind of like a variant of spinal anesthesia. Someone who couldn't tolerate general anesthesia, you had to do an upper extremity procedure. Big problem with this, injuries. Upper limb is pulled too hard, football players, blows to the shoulder. The other one that's interesting, that first one we learned about, is where crutches are. So if you ever were on crutches, they have what are called axillary pads. It's a misnomer because that sort of curved area is not supposed to fit into your, people lean on it and they create, in the old days we called it a nerve palsy. So you're supposed to, that is if they're fit properly, they fit in here. I have a lot of students go into physical therapy classes and physical therapy in a career area. That's part of it, crutch fit. I mean, everybody, in the old days, we used to, when we'd admit patients, put them on crutches, you keep them in for a couple of days, send out a PT for crutch fitting and crutch work. Now it's the same base stuff. Median nerve, as you can see, that's the carpal tunnel. Wrist we saw some buttes. The ulnar nerve, again, that's they talk about claw hand, but that's the funny bone right by the epicondyle, etc. Wrist drops. I mean, these are all intoxicated person falling asleep. The arm drape, that's what I was talking about. It's a little bit like the cast. It's there. The lumbosacral plexus, almost done with this. Significant areas of overlap. And so now we separate them, okay? If you want to look at them together, lower limb, abdominal, pelvic areas as well. They separate them. L1, L4. When we talk about innervations in the lower extremity, particularly the thigh, I mean, it's not necessarily two regions like anterior and posterior. Thigh has three. you have this. You have a medial region, an anterior region, and a very large posterior region. The lumbar plexus is medial. These are the groin muscles that people refer to. They're the adductors, some other muscles. When you hear about an athlete having a pull or torn groin muscle, this is the area. And they're a long time. Any gym, all the machines are out. You know, where you can pull in, pull out. The anterior muscles are for this. The anterior group is for extending your leg. They're extraordinarily important in walking, obviously. And so that has to do with what's called, and mostly you're impacting the quadriceps. So if you go back to your A&P muscles, you have rectus femoris, vastus medialis, vastus lateralis. They're named enormous. And there's one of them underneath it called vastus intermedius. And that's the one that inserts into the knee capsule. So if you have a knee injury, one of the things we do, this is where muscles play a role. One of the things we do are called are straight leg braces. That's the standard rehab for knees. People lie on their back with weights, progressive resistance exercises, pulling their toes toward their nose, and bring it up because you're really tensing that group. So that when we see a drop like that, that could have points to what's called the femoral nerve. Quadriceps, some skin, obturator is the nerve that goes into that through the obturator frame. And if you remember the anatomy of the hip bone assembly, that obturator frame is formed mostly by the pubic and ischial bones and goes into those adductor muscles that are there. They're huge. And then there's a lot of other ones that play a role into it that are there. And here they're demonstrated. That would be the obturator nerve. This would be the femoral nerve, which goes right underneath the inguinal ligament. So sometimes it's impacted when someone has a sports hernia or what's called a rupture. And you can see some of the other branches there. It has a very, very long branch that runs all the way down, as you can see, almost to the medial aspect of the foot. It's called the greater saphenous nerve. You'll see that name again when we start looking at blood vessels. Very, very famous veins are called the saphenous or saphenous, depending on who's pronouncing it. They give you what it goes to. And then the sacral plexus, everything posterior, the buttocks, okay? Big muscles that are there, okay? The lower limb, pelvic structures, the perineum, the area, the anogenital area. And mostly the big player in this is the sciatic nerve. It's if you remember the ear and hearing, we had a name, we used to call it the auditory nerve. It was a misnomer, because now we call it the vestibulocochlear nerve. The sciatic nerve is like that in the sense it's two nerves wrapped in one. Longest, thickest nerve, hamstrings, one of the adductors, the adductor magnus, almost everything in the leg and foot. And it has two nerves, the tibial nerve, which handles most of the posterior and plantar aspects when you get to the foot, and the fibular nerve, which has a lot more to do with the latter and the lower extremity, your compartments based on muscles. When you get down to the leg area, you have posterior, you have a lateral area, and you have an anterior lateral area. Your shin kind of dominates. And so those are the fine, and that's really what you need to know, that the tibial nerve, it does give rise to something called the sural nerve. Sural is an old term we used to use for calf. Eventually gives rise to the medial and lateral plantar nerves, that's the foot. The common fibular, anything that says common always branches. Okay, innervates the knee, areas of the skin and leg, muscles of the leg, all of that. And then we have gluteal muscles for the gluteal nerves, etc. So that's another portion that comes off that plexus, the pudendal nerve, that's perineum. So you can see how elaborate it is. And if you remember back to bone anatomy, you had greater and lesser sciatic notches. That's a big nerve. That's there. So you can see both of the segments that are there as it goes through those notches. You can see now some of it will carry down, but there's the divide. And a very interesting area anatomically is the popliteal fossa. That hollow areas behind big joints are fascinating. Axilla, cubital fossa, popliteal fossa. And right in there, now that's the tibial nerve. And what winding around, it bifurcates here into the the deep and what's called superficial fibular nerves. What's interesting is that they wind around here. The one that's going to be the deep fibular nerve and the superficial nerve, we see that interesting divide right around the neck of the fibula. So if you ever had a cast on your leg, casts are called short leg and long leg. Long leg casts go above the knee. Short leg casts go here. Where do you put it? And there's some nuances. The mistake is, when we used to train residents, was putting on a cast when I was training. People would put the cast up too high here. The trouble is that nerve wound around the neck of the fibula. So your idea was to palpate the head and neck of the fibula, 2 finger breaths and a cast with the mark. Because if not, then you get what's called a drop foot. Whenever you cast or immobilize somebody, it's got to be specifically in the area. You put the cast on because it's hard to rehabilitate it. But if you compress a nerve, now it's really hard to do. So that's another little interesting nuance of this. They're just showing some pictures of it, elaborate discussions, the major players. This is the part you need to know. Okay. And femoral nerve, herniated disc, pain in the medial thigh, sciatica. I'm seeing my chiropractor this afternoon. Okay. And not a whole lot. Dermatomes, this is when you do testing, if any of you are going to go into this, and you start to take, I always use a sterile needle for sharp and dull, and because it's disposable, you'll be testing reflexes or testing sensation. So when you do a knee jerk, L3, L4, L5. When you do the Achilles, L4, L5, S1. So it gives you a clue. If you see an irregularity, there's a problem here. It's all little bits of information to make a diagnosis. That to me is the most interesting and the most challenging part of medicine. And innervating muscle and nervous joints by, thank goodness we're done with nerves. The next major topic is the dog is at Camp Biol. He's on vacation. Because it's a holiday, you have to have 3 days. It's a 3-night minimum. We would have to leave the dog in the house for 12 hours without imagining what we would have found. It's a very big dog. On his hind legs, his paws go up. Elongated. Moving on. So that is that part. So what I decided, just for you're doing the lecture thing online. I take it you get either assignments or things to listen to and to do that deal. What are you doing now? I always ask this.
Endocrine.
You're an endocrine, okay. Nothing in anatomy for endocrine. Endocrine is the least anatomical system there is. Name that gland. Pineal gland, pituitary gland, thyroid gland, thymus gland, pancreas, very important. Okay, that kind of reproductive gland. Happy dance, done. Not a whole lot left in the gland, but for a tiny system, very important. So I never do that. Okay, it's like the immune system. That's another one of the systems I never. If you have questions about it, I love those systems because the endocrine system, diseases, the single most important disease that anybody can learn about, diabetes. Diabetes. Every time I tell students, when I teach the advanced, and I have a lot of pre-med students, tell them the same thing. Nursing students do the same thing. Every time you have a new patient encounter, nursing students do this routinely because they do med cards. They write, they see, okay, we're seeing Mr. or Mrs. So-and-so. They write down the meds. They look up the meds. Every time you do that, put the name of the medicine in a book, in a little notebook, put it on your phone. Put a tally mark. You don't just write it 10,000 times. Just put a tally mark next to it. See how many people are on Atorvastatin. See how many people are on, like the amlodipine or losartan. Gazillion. Those are the medicines you need. Anything that people aren't alive, you need to know. How many people are on insulin? Same thing with diagnoses. Diabetes, osteoarthritis, cardiovascular impairment, heart disease, all those things. Those are the ones you need to know about. When you get somebody who has something, an oddball, like Sjogren's syndrome, which is an offshoot of an immunological disorder. Interestingly, Venus Williams has that. When she didn't play well even in her prime, it was usually because that was flaring. Those are relatively rare. You do what everybody else does. You look them up. Oh, I never, you hear that once. Anytime as a clinician, if there's something you encounter on a yearly basis, you should know about it. That's more common than you think. It really is. It's surprising. These are all little nuances I learned over years of training with absolutely brilliant people, much, much smarter than I would ever. So, apropos of that, down here, there's really very little in that. Is I cooked up, I just wanted to give you a share, before we do the heart, a smidgen of blood anatomy. Just because when we do the heart, it's part of the picture. It's, to me, this is another one to me, is much more of a physiological thing. We do not do like punctures it's by design. It has something to do with liability, as things always do. For years, we couldn't use, even though you can go out to Giant Eagle and get a finger stick thing to test your blood if you're a diabetic, or for fat levels, or whatever, for keto levels for people on keto diet. Anybody can do it. They don't let me do that in the lab in AP2. They let me do that in the lab in advanced physiology. Sorry, guys. But I think it's important, and you're doing blood typing and things like that. You'll get to it. If you haven't had that yet, I'm very knowledgeable about this area. I'll flatter myself, and not for a good reason. So I'll give you the skinny on this without going crazy. Okay. Yeah. Blood is a connective tissue. Everybody, how could it be a connective tissue? It's not hard. There's nothing in the rule book that says connective tissues have to be solid or semi-solid or soft. Blood is liquid. The difference is, remember what tissues are: cells, ground substance, fibers. Well, the matrix, the ground substance, and the fibers happen to be liquid. The ground substance is liquid, and the fibers are dissolved in the liquid. They're in their soluble state. They have a very important name called fibrinogen. They're protein fibers. The whole idea of your blood clotting, for whatever reason, and I'm not going to bore you with the clotting cascade or anything along those lines at this point in time. Basically, those strands, the whole clotting cascade activates a system that enables those fibers to go from soluble, dissolved in the liquid of the plasma, to insoluble. And of all things, guess what they do? They form a fishnet. You look at it microscopically, it's exactly what it looks like. And what does it do? It traps red blood cells. Clot. That's the easiest way to view the clotting cascade and the end product of it. The transition from what's called fibrinogen. And ogen is a term to be familiar with going forward. Ogen are precursors. Proteins that we use all the time when they're necessary are typically in the inactive form, called the ogen form. You'll hear about them in digestion. Trypsinogen, chymotrypsin, pepsinogen. They're precursors, because if they were released in their active form, they would indiscriminately gobble things up. If fibrinogen was inadvertently activated to fibrin, the name that it has, you would have clots, and people would have a clotting disorder where they would clot excessively. Most clotting disorders are a failure to clot adequately. So a little bit about that. Yeah, it transports stuff around, regulates pH, temperature, etc. Protects your immune system's pathway of getting white blood cells to where it's supposed to go, here. Okay. So big number one on the hit parade, oxygen, nutrients, waste removal. Okay. Those wonderful endocrine hormones. By definition, endocrine hormones transit by the bloodstream. One of the definitions of endocrine. Remember, an endocrine gland has has a network of blood vessels around it, and when it secretes, it's sucked up right into the bloodstream. Temp, pH, buffering system, fluid volume by that. Blood loss, that's the whole clotting eye, infection, all the what they call the agents of immunity, circulating antibodies. If you were immunized for COVID, okay, you now carry some of those antibodies for X amount of time, and you are pre-programmed to make those antibodies rapidly. The whole other issue as to whether or not, my question is, why do we have to keep getting more COVID shots? If it was, if all of you were immunized for polio, I'm not thinking anybody got polio. The polio's still there. So the quality of the immunization is the question. It has some of the same problems associated with influenza. If you didn't have micro, it's a virus, just as the influenza viruses are, that mutate relatively rapidly. So there's some issue as to why even bother with trying to do things, but I digress. White blood cells, certainly that's what carries it. Fluid, the plasma, everything else we call them formed elements. Why don't we call them cells? Because they're not traditional cells, with the exception of the white blood cell. The only traditional cell, meaning a cell that has a nucleus, is the white blood cell. And we actually describe them by way of the appearance of the nucleus, which is interesting in and of itself. The red cells were certainly cells when they were born, but they are after their nucleus has shed. If you're seeing nucleated red blood cells in the bloodstream, there is a problem. So part of their maturation process, which is critical, is the understanding of what makes different kinds of anemias, which is part of this chapter in more physiology, is the shedding of that nucleus at the appropriate time. And that's a big deal. Context. Unfortunately, I've had, in 1993 and 2000, one when I was 42 years old, when I was not yet 50 years old, I had 2 major ulcer surgeries. Because of the second one, I had so much blood loss, I've had unbelievably large number of transfusions. So this is my context for understanding a lot of that. That is there. Thankfully, I don't suffer from any of those problems now. I'd rather give ulcers than get ulcers. It's better to give than receive. I think it's fair. Okay. So what do we got in there? Red cells, no nucleus, so we call them a formed element. White cells, leukocytes, leuco for white. They're really not white. But because they're not red, they call them initially white cells. And platelets, which are fragments, okay, of cells, fragments of cell membrane, fragments of protein. So they're really not cells. They come from a giant cell that's kind of, it's like you were making a wonderful sauce. You were making a hollandaise, okay? You were making a Sauvignon. Okay? So you have to make that. If you didn't know, you make that with eggs. Sometimes when you cook eggs too hard, they scramble. So you run them through a strainer. What comes out is a smooth sauce in classic cooking. Okay? That's really what platelets are. They've come through a strainer. A lot of reticular fibers located in the bone marrow, and little fragments come out. Thankfully, they're not lumpy. So what does that leave us with? And this is the classic example. I will go back to this. Oops, I'll go forward to this. This is what happens in a blood, and this is the context I want, because we need to understand what happens with the heart, and you have to understand kind of when there's problems associated with this. Okay, if we take out a tube of blood, This is if you go here and twice a year here, routinely they have a blood drive. Easy, twice a year. What they do when they take out that blood is it's not, they took out a pint of my A positive blood, okay, it's unusual for them to just give that pint of A positive blood to somebody else, though that does happen. That's called holding. They spin the blood down with a centrifuge, nothing magical. And when you centrifuge a good sized tube of blood, this is one of the experiments we do in the advanced physiology lab. We use a capillary tube, not a big test tube. So it's a tiny amount of blood, a milliliter or so. You have basically what centrifugation does is the heaviest stuff goes to the bottom. So you get the red cells, which are the heaviest, packed. And indeed, that's what we call this. Packed cells. 98% of transfusions that are given are packed cells. Somebody's in a terrible accident, they're bleeding all over the place, they'll put them in whole blood because they've had a lot of blood loss. What they will do then subsequently is once they get them stable and stop the bleeding because it keeps pouring out, at that point you'll start adding packed cells and plasma and different other fluids to adjust it. Okay, you don't want to waste all those elements. I hate to put it the term waste, but you can utilize it better. The plasma, we can extract proteins and things from the plasma that are useful, that are there. Plasma injections, we've done a lot. Okay, and then because there'll be a lot of antibodies that are in there, and then the white cells and platelets are here, and you can extract those. It's called a buffy coat. It's got like an off-white or a buff color. All that from centrifugation. And because it's a uniform tube, what we can do is we can measure. It's a uniform tube. Effectively, it's a cylinder. If you measure the whole length, you will find, and the buffy coat is typically negligible, that the typical area is 55 to 45. That proportion of red cells to total fluid is a very famous name. It's called the hematocrit. In a hospital, doctors, nurses are always interested in going, what's so-and-so's hemoglobin or what's the hematocrit? We just stop doing multiple blood tests. You don't need to. You just do what's called H&H, hemoglobin and hematocrit. You don't have to recheck everything. When you're really interested in this is the measure for anemia. Okay, so that's really what you start with. So the hematocrit, percentage of blood volume, that's red cells. That's the measure. Because the red cells carry the oxygen. In men, typically healthy, 47 plus or minus 5. In women, 42 plus or minus 5. Women have a little lower number of red cells because red cells are proportional to testosterone plays a role. And women make very limited testosterone supplements. Other than when you get in the adrenal gland, you'll see that in women in the adrenal cortex, okay, that's where the limited androgen or testosterone-like precursors are found in women. So that's one of the reasons, as well as menstruation. Okay, and you can see the numbers that are there. We take this value and to approximate hemoglobin, we divide by 3. So men typically 14 to 52. I mean, that would make it 42 to 52. So for men, a hemoglobin of 14 to like 17, normal. For women, proportionally a little bit less, 12 to 15. Mine runs high 13s to 14 through all those surgeries. Every so often I get excited and show you my blood tests. I can't violate any laws by showing you my own blood tests. So the plasma, water, lots of stuff. The aforementioned hormones, waste products. Proteins by definition are soluble for the most part other than structural proteins. So the fibrinogen protein is a structural protein normally that is in its precursor state and dissolved. All of these other things are there sort of implicit, they're obvious. Proteins are what we have the most of all the things in our blood, whether it's nutrients, whether it's ionic particles, waste products, etc. Okay, they are mostly made in the liver. liver disease, and we sort of go back into this again a little bit when we start to do digestive, where the liver is found. When your liver is damaged, your blood won't clot because you don't make clotting proteins. You don't make albumin, which is the most abundant. You can't fight infection because you're not making immunoglobulins. So all of those play. The liver is, when the liver is damaged, it's big. So there's a lot of things, viruses, various kinds of infection, toxins, certain medications are hepatotoxic or liver toxic, and certainly the number one on the hit parade, alcohol. So the albumin is a carrier molecule, and when you get to physiology, this is a big player. It's called osmotic. Osmotic pressure is what holds the two forces going on. Your blood pressure, the force of your blood rushing through. You have a series of tubes. When you get to capillaries, those tubes have openings. It's part of our course, you see the anatomy. They have little openings and liquid seeps out. So normally, if you didn't oppose that force, by the time the blood got to capillaries, most of the water would be out. We have proteins. Proteins act as a column. They hold water. So they oppose that. So you only have, once enough fluid runs out, then the force of proteins holding the fluid in encourages fluid to be absorbed at the end of the capillary. It's really the basis of circulatory physiology of the capillary. Stuff goes out as it's going, sorting in the bed. By that time, once the fluid goes out, it reverses the process. Out with the oxygen, out with the nutrients, back into the wastewater. What happens when somebody has liver disease, and if you know somebody who has a failed liver, they're filled with fluid. There's nothing holding it in. By gravity, it goes to the extremities. They'll have a great big belly. And that it isn't because it's necessarily fat, it's fluid. If you see a war-torn area, little kids who don't have enough nutrition, of spindly arms and legs and fluid in their belly. It's called ascites. It's a famous name. ASCIT. And a kid's overweight. No, he's not. First thing that you ship to a war-torn area or a natural disaster, foods with proteins. That's why most of the damage from natural disasters and war-torn areas came after from disease. Now we're a little bit more on top of that. So albumin, big player. The other ones are globulins. You'll get into those in lecture. Okay, they transport fats and things like that, but particularly the gamma globulin fraction, which is antibodies. And then lastly, the fibrinogen. I just wanted to give you the lowdown. And this is just, there's a limited amount of survival. These are not live forever cells. Blood cells start in the bone marrow. Okay. And what you'll see is the vast majority of white blood cells have a very limited lifespan. Red cells last 90 to 120 days. So the optimal time to make sure that you've used blood that you have donated by way of the blood bank is roughly 2 months. And this is just a picture, real micrograph. The red cells, that you can see the platelets are little fragments that are there. Classic peripheral smear. So you can see the white cells are not white, they're just not the same color when you stain them. Nuclei, and we look at the nuclei to identify the cell. So you'll see, and you get this, again, more lecture than lab, particularly in immune. This is the classic, the most abundant cell is called this. It's called the polymorphonuclear leukocyte or neutrophil. That's the most abundant of all the white cells, about 55% average. Next most abundant is this called a lymphocyte. This is the one that most of the ones that you see in a peripheral smear are probably T cells, if you get to that in immunology. So neutrophil here, platelets are tiny, neutrophil here. How do you know a neutrophil? It has a lobed nucleus that's sectioned. Eosinophils have red granules. That's what the EO stands for. They generally have two lobes. It's not, it's one nucleus. It's a nucleus that has folded for whatever reason. Best analogy for folding a nucleus? I love this. Balloon puppets. You know, did you have a birthday with balloon puppets? Anybody? Oh, it's the wrong age. Didn't you ever see those things? Like, yeah. Like balloon puppets. Folded nucleus. Monocytes have a big sort of chunk. They call it a kidney shape or a big U shape. They're the largest. That's just some of the things. And the rest of this is not that terribly consequential for our purposes that are there and how it carries the blood that's there. When it sheds the nucleus, its design is such that it creates a vast amount of surface area. So a typical red blood cell like this will have, it's basically made, it's a membrane package of an interesting shape that's filled with one protein, hemoglobin. And the hemoglobin, I mean, we're talking each red blood cell has about 250 million molecules of hemoglobin that each can carry 4 molecules of oxygen. So each one of these cells carries a billion molecules. Imagine how much oxygen you need. In a milliliter, you have 5, in a microliter, millionth of a liter, you have 5.5 million of these cells, typically. Each one that can carry a billion molecules of oxygen. If you do the math, it's astronomical. So it reversibly bonds. You can see the hemoglobin numbers I was talking about. The heme is the pigment. And what you do when you study this about how red cells break down anatomically, you look at a classically studied molecule, alpha and beta chains, 2 and 2. Each one has this heme unit. The heme unit is something, it's a protein iron compound that's hard to dispose of. So that's when people have excessive amount red cells or red cell breakdown, where there's a blockage in the liver which processes them, you get a classic appearance called jaundice. Babies are frequently born with jaundice and have to undergo ultraviolet light because there's an incompatibility. It's not as bad as something called erythroblastosis fetalis. That's a different disorder. So that's another one that's there. And so that's what those heme. These are the part that are hard to get rid of. The iron you can recycle. That's hard to recycle. The heme unit itself is the hard part. It's a very interesting. It's a well understood structure. These are the numbers that are there. Red bone marrow produces that. You might remember from your bones. Red bone marrow is kind of everywhere until you're an adult. And then the red bone marrow is kind of limited to the flat bones like the sternum, the iliac crest, and maybe a little in the hip and shoulder assembly that are there. And then this is all physiology stuff, how they develop from stem cells. One of the things we utilize scientifically to see if you're making too much or not enough. How are you? Okay. One of the things we look at to make sure we have enough or not are called reticulocytes. So what happens when we do a blood count, you also get something called a reticulocyte count. So you order with CBC, complete blood count. A complete blood count has red cells, white cells, hemoglobin, hematocrit, and they do a retic count. So about 1% still have little bits of the endoplasmic reticulum and ribosomes. That's where they get their name. Because they're not fully matured. If you have too many of those, you're pushing out immature forms. If you don't have enough, if you have a low number, they're overly mature. All that means is something's wrong. It's either pushed out too fast or something blocking them escaping. So that's, again, part of the diagnostic acumen that's there. And it's what they look like. They get smaller. So we classify different anemias, whether they're too small, typically not enough iron, called microcytic, or too large, macrocytic. Most common reason for too large, deficiency in B12 and folic acid. B12 anemia is very, very famous. It's called pernicious anemia. It's more common than you think. Treatable because we can use B12 injections and nasal gel for that matter. So that's interesting. And all this other stuff. Erythropoietin is what's the kidney plays a pivotal role as well. That's why one of the things we see with people with on dialysis or kidney failure, read that as mostly diabetics. You did not know 75% of people on dialysis, they have anemia. And so we can manufacture this genetically now as a genetically modified chemical called Procrit, not by its other names. And it's utilized to bolster people to deal with hypoxia and things along those lines. Blah, blah, blah. Almost done with this, and let me see what time it is. Good, taking a break. Then we're going to do it. We'll go in there and show a little heart and dissect an eye. So here's the erythro. This is one of the things they used to use this a lot. You're here at the right time. What's going on in France on Peacock or USA Network? The Tour de France. The most prestigious of all, it's the most ultimate endurance challenge. 23 days, 2,000 miles, up and down mountains. So the blood doping, when you talk about cheating, there's more cheating in this than just about anything. For years, people would suck out their blood, spin it down, and inject themselves with packed red cells to increase that. I mean, because you're sitting up there at 10,000 feet elevation, trying to cycle up a mountain, not easy. That was a famous story about Lance Armstrong, who won that event 7 times, and then they were all vacated, which is a whole other story that's part of it. Let's see, we're not going to do that part. Or this is how they get rid of it, the iron and the heme. Blood loss, that's against more physiology. It shows you some of these you see these different kinds of anemias where we're getting sickle cell and variations of it. They're also interesting. This is one of the problems, the secondary polycythemia. Normally that occurs at altitude. You have a subtle increase. If you're living, I have a stepdaughter who lives in Denver. Surely they've acclimated. They've been there for 3 years. Okay. But this is, people who are blood doping or using erythropoietin, effectively GMO products would have this. Sometimes it's cancer related. That's true. Polycythemia. Your blood is too thick. When you're anemic, it's too thin. Not enough red cells. Red cells give it the bulk. The viscosity is altered. When it's too thick, harder for your hardest to work harder to push you around. And that's the blood doping. And to me, this is more physiology. You'll go through all of these and what the roles are because you'll do this in immunology. I'm trying to hear anything else I want to cover in this. And then again, this is the different cell lines that are there and some of the diseases that are associated with it, both viral and otherwise. This is the part where what's in those platelets, this has to do with the clotting aspect that are there. And then all you typically do is you evaluate, typically they'll just say platelets normal or adequate. Those are the fragments, it's how it breaks off. And it goes through what happens. And then this is something that you probably look at in lecture coming up, having done it 1,000 times. This is, there are 2 pathways. When you cut yourself, this is the least frequent. It's very fast. Cut yourself, it releases a chemical called tissue factor. We used to call it tissue thromboplastin. And very rapidly, it goes down to this level, which very, very rapidly initiates the clotting. The vast majority of clotting of your blood is repair. Your vessels are roadways. Like any road, the more they're used, they get little bits of damage in them. We live in the state that has the worst roadways in the world. I'm confident. We have names for the potholes. Effectively, the intrinsic pathway identifies little potholes by collagen demonstrating and proceeds to seal them up and repair them. So it's happening all the time. This is the pathway that, unfortunately, when someone has heart disease or blood vessel disease, this is the pathway that's impacted. Because what happens, the more fatty deposits, which typically is what they do, they tend to make the hollow tube have a little bulge. That bulge creates an area of turbulence for clotting. It also creates an area where it begins to break down and becomes inflamed. So there's a lot of different ways to approach it. Oh, there's that fishnet. Love that. One of my favorite illustrations. And that's all the stuff, the pathway and how it matures. And let's see if any, and these are disorders. Again, that's more of something we do. Those are called petechiae. There's the liver playing a role with clotting and different types of bleeding disorders, which are mostly genetically oriented, that are there. And this is the transfusion nuggets that are there. When I was quite sick, somewhat amazing that I'm here. Normally, most of you would have between 15 and 17 hemoglobin. Mine was 5 internal. Very surprised I was able to move. And let's see. And then they do the whole, and I think I'll skip that. If you folks are interested, let me know next week if you want me to review any of the clotting aspect of things. And the, not the clotting, but also the clotting, of course. But this type of stuff, the ABO stuff, is very, very interesting. It's more than just that. Those help because you're less likely to have something awful happen as long as it's compatible blood. It doesn't exclude it. We don't just look at A and B or O and positive or negative. There's a lot of other factors that are involved for the blood bank takes. And typically the blood bank for an easy match can do it right away, an hour, 2 hours. For a complex match like I did after all these transfusions, 2 days, get the blood on. Because there's so many other factors from foreign blood creating antibodies. It's a foreign substance. Your body's always going to react to it. It's a matter of the degree that it acts to it. The only blood it doesn't react to erroneously is your own. That's called an autotransfusion. People used to use a lot of directed donation. Oh, my Uncle Charlie's got the same blood type I do. It's called a directed donation. Statistically, that is more of a problem than blood bank blood. Doesn't mean Uncle Charlie was fooling around. You shouldn't. Okay, picked up some disease. But there's a greater likelihood than with a blood bank. And so since 1987, blood bank blood is very, very safe, comparatively speaking, unless there's been some major untoward error. My first wife had 2 units of pack cells because she had, we were trying to get pregnant, weren't able to do that. She had her ovaries wedged back in '81 at Shadyside Hospital. Brilliant doctor, brilliant. The blood they gave her probably exposed her to hepatitis C. She had a massive bleed inside. They had to do something about it. They found out she had an interesting clotting disorder that's genetic it's a variant of what's called von Willebrand's disease, which is a platelet disorder. So let's see. Yeah, I'm not going to go into all those. Sorry. I'm going to say we're going to go in the other room in 15 minutes. We'll do the eye dissection. I'll introduce the heart in hopes that maybe we can dissect the heart next time. Show you some of the techniques.